Hello students, welcome to class 12 physics. In this video we are going to solve numerical of the textual exercise of chapter number 6 electromagnetic induction. Numerical number 3. A long solenoid with 15 turns per centimeter has a small loop of area 2 centimeter square placed inside the solenoid normal to its axis. So here we are having a long solenoid and there is 15 turns per centimeter. Inside the long solenoid there is a small loop which is perpendicular to the axis of the solenoid and its area is 2 centimeter square. If the current carried by the solenoid changes steadily from 2 ampere to 4 ampere in 0.1 second, what is the induced EMF in the loop while the current is changing? So here we need to find the induced EMF in the loop that is placed inside the solenoid. So we know that induced EMF equals to minus d phi by dt. We are knowing this equation. So we need to find first phi. So here because of the magnetic field of solenoid, magnetic flux gets linked with the small loop kept inside the solenoid perpendicular to its axis. As you can see over here, the current from the figure, the current is passing from the upper side, the current is coming out of the plane of paper, and from the bottom you can see that current is going into the plane of the paper. So when you curl your fingers of the right hand, then the thumb direction will be towards the right hand side. So this shows the direction of the magnetic field. And the area vector of the small loop is also along the right hand side. So you can see the area vector and the magnetic field both are parallel to each other along the same direction. So theta will be 0. So the magnetic flux is equals to AB cos theta, and taking theta equals to 0 degree we get AB cos 0 degree, that is AB. So magnetic field for the solenoid, that is mu 0 n I. So we got phi. Now using the equation of the magnetic flux in the induced EMF equation, that is epsilon equals to minus d phi by dt. So minus d by dt into phi, that is a mu 0 n I, and here small n is nothing but that is number of turns per unit centimeter, that is n by L, and n we are having 15L is 0.01 meter. So here we are having a mu 0 and n by L constant, or we can say small n is constant. So taking it outside and taking derivative of the current, because here the current is changing with respect to time. So minus a mu 0 n di by dt. So placing the values of a mu 0 n and di by dt. A, that is 2 into 10 raised to minus 4, mu 0, that is 4 pi into 10 raised to minus 7, n by L, that is 15 upon 0.01. And here change in the current with respect to time, that is it changes from 2 to 4. So in 0.1 second. So 4 minus 2 upon 0.1 gives di by dt. So when we calculate this, we get minus 7.536 into 10 raised to minus 6 volt. Taking its magnitude, we take epsilon in the modulus. So we get its value as 7.536 into 10 raised to minus 6 volt. So students, you may copy down this numerical. Now let us solve numerical number 4. A rectangular wire loop of sides 8 cm and 2 cm with a small cut is moving out of a region of uniform magnetic field of magnitude 0.3 Tesla directed normal to the loop. What is the EMF developed across the cut? If the velocity of the loop is 1 cm per second in a direction normal to the longer side of the loop, for how long does the induced voltage last in each case? So as you can see in the figure, the rectangular loop is placed in the magnetic field and the magnetic field is going into the plane of the paper, and as you can see the direction of the velocity, the loop is moving in the upward direction. So from this figure we can write VPQ, that is here we are going to find the induced EMF of this small cut over this small cut. So VPQ equals to VPT plus VTS plus VSR plus VRQ. And over here for side PT we can see that it is not in the magnetic field region. So for that B equals to 0. So for PT it is equals to 0. For the sides TS and RQ, length is parallel to the velocity. So that is also 0, because as you can see here the formula is PVL sin theta. So here BVL sin 0 degree. So it becomes 0. And for the side SR we will be having BVL. For the side SR we are having L, BVL, because here the length and the velocity both are perpendicular to each other, making sine 90 degree, which is equals to 1. So VPQ is equals to BVL. Substituting the values of the magnetic field, velocity and length, we get the value as 2.4 into 10 raised to minus 4 volt. So student, you may copy down this portion. A rectangular wire loop of sides 8 cm and 2 cm with a small cut is moving out of a region of uniform magnetic field of magnitude 0.3 Tesla directed normal to the loop. What is the EMF developed across the cut if the velocity of the loop is 1 cm per second in a direction normal to the shorter side of the loop? For how long does the induced voltage last in each case? Now see, the same thing is there, but now the loop is moving towards the right hand side, that is it is normal to this shorter side, and we need to find again the induced EMF for this small cut. So from the figure we can write down this equation: VPQ equals to VPT plus VTS plus VSR plus VRQ. So for the side RQ, here the magnetic field is 0 because it is out of the portion of the magnetic field. So it is equals to 0. And for the sides SR and TP, the length is parallel to that of the velocity. So it is equals to 0. So we will be finding the voltage only for the side B, because it is perpendicular to that of the velocity. So that is equals to BVL. But here the length is indicated as small b. So it is BV small b. Now putting the value of BV and small b, we get the value as 0.06 into 10 raised to minus 3 volt, which can be written as 0.06 millivolt. Here, EMF induced in the longer side will last for time t1, in which shorter side comes out of the magnetic field. So, we can write V equals to B upon t1, because we are going to find for the time over here for how long does the induced voltage will be lasting. So for that we will be using the equation of velocity. Velocity is distance upon time taken. So time taken is equals to distance upon velocity. So T1 equals to B upon V. Here B is nothing but the shorter side length and velocity with which the loop moves. So putting the value, we get 2 into 10 raised to minus 2 upon 1 into 10 raised to minus 2 equals to 2 second. Similarly, EMF induced in the shorter side will last for time t2, in which the longer side comes out of the magnetic field. Hence, V equals to L upon t2. So t2 is equals to L upon V. Again using the equation of the velocity, taking time as subject, and here the distance is taken as the length of the rectangular loop. So L upon V. Putting the value of L and V, that is 8 into 10 raised to minus 2 upon 1 into 10 raised to minus 2 equals to 8 second. So time taken is 8 second. So we found for how long this induced voltage will last for both the cases. So students, you may copy down this numerical.